Morning, everyone. Today we're going to go over valence bond theory on BrI5, also known as bromine pentaiodide. Both of these are from the group 7. Therefore, there is a total of 42 electrons, 35 of which coming from the iodine and the other 7 coming from bromine. So first things first, we're going to draw the Lewis structure. For bromine pentaiodide. Bromine is going to be the central atom, and we're going to have 5 iodine attached. Now we find that when the iodine are given their electrons, that there is a lone pair of electrons to make up the full 42, and those get placed right on the central atom bromine. This specific structure of 5 bonding pairs and 1 lone pair is going to play a significant role in which Vesper diagram should be drawn. Therefore, looking at the Vesper diagram of BrI5, again we find that there's 5 bonding and 1 lone pair of electrons. This is going to be an octahedral, and more specifically this is going to be a square pyramidal. The octahedral being the electron geometry, square pyramidal being the molecular geometry. So now when we draw this, we again put bromine as the central atom. But what's going to happen is we're going to get a rectangle drawn, and that lone pair is again going to go straight with the central atom. We're going to have wedges here to show a 3-dimensional model. And every angle is going to be less than 90 degrees. This is what gives us the square pyramid shape. Furthermore, as we'll see more in depth on the contour diagram that will be drawn, the lone pair to bonding pair repulsion is greater than the bonding pair to bonding pair repulsion, which is pushing both of these wedges. Okay, so now we're going to look at the energy diagram for this molecule. And we're focusing now on bromine, the central atom, which has 7 electrons. Okay, this is going to be the ground state. And what's going to happen is the energy is going to go towards the promotion. And the two electrons that get promoted are these two here. We're going to fill in the rest of our electrons now. This is going to be the excited state as well, which will give a star to the bromine central atom. Alright, so as you can see, this is the excited state of bromine, and now we're going to move on to the hybridization of it. This is going to be an sp3d2 hybridized. And we'll see that this non-bonding pair gets placed too far. Will get placed right here. sp3d2. And then these here are all bonding pairs. So these are going to come from the 5p, that is a 5, not an S, because of iodine, in which we have 5 total in our molecule. Its 5p is also set up for the group 7. And what's going to happen is this electron here is going to get distributed down to fill all of our bonding. Oh, forgot one there. There we go. And this is known as the bonded state. For bromine. Okay, so lastly, we are going to draw our contour diagram for bromine pentaiodide. And again, as a note, the lone pair bonding pair repulsion is greater than the bonding pair repulsion. So let's go ahead and draw it. Alright, to draw, again we place bromine as the central atom. And then let's go ahead and add in our sp3d2 orbitals. And our electrons. In which they all have electrons in the sp3d2 orbital. Now let's add in our 5p representing our iodides, in which they bond right there with the bonding electrons. Okay, each angle is 90 degrees. I'm sorry, less than 90 degrees. And again, as you can see, we left the lone pair. which gives us the lone pair to bonding pair repulsion as greater than the bonding pair repulsion as previously stated. I do want to make another note that all of these bonds here, the bonding pairs, they're actually going to be sigma bonds. This is the molecule from the molecule kit built. And again, as you can see, here's the lone pair on the bottom. Each one of these here are going to be your iodine. This is your bromine. And each one of these light gray, represent as the bonding pairs. And lastly, from the Vesper application, we see again the lone pair of electrons, and you could actually tell that the angle here is being repulsion, which is that again less than 90 degrees.